In space, everything spins for a reason. It's not magic, it's science. Rotation is the secret engine of the universe. It speeds up ice skater stars as they fall apart, flattens galaxies with centrifugal force, and creates black holes that pull space-time apart and send out jets. Small early nudges, tidal torques, spin up halos of dark matter. Disks form and move angular momentum outward, MRI, bars, resonances. Planets lock onto their suns, asteroids spin around in the sun's light, YORP, and close pairs lose their spin through gravitational waves. We'll look at how spins begin, grow, line up, flip, and sometimes end in atoms, worlds, stars, galaxies, and other places. Conservation of angular momentum. One rule that shows why everything spins is this. A system's total spin stays the same when nothing outside it gives or takes away rotating push. If you look at kids on a spinning chair and galaxies 100,000 light-years apart, you can see that angular momentum stays the same. Imagine a cloud of gas in space that is falling apart. At first, it's very big, fluffy, and not moving much. As that cloud is pulled in by gravity, it gets smaller. To keep the same overall spin budget, the spinning speeds up. You've seen the human version on ice. A skater pulls their arms in and spins faster, making everyone gasp. Space does that on a large scale. What actually conserves here is a product of how much stuff you have, how it's distributed, and how fast it's turning. Spread the same mass farther out and the moment of inertia grows, which would slow a given spin rate if nothing else changes. Squeeze that mass inward and the moment of inertia drops, so rotation must quicken to keep the same overall spin. This is why collapsing clouds flatten into disks rather than just falling straight to a point. As the spin rate rises, a sideways outward centrifugal effect builds in the rotating frame, balancing part of gravity. Gas can still drift inward, especially if it can shed heat and move angular momentum around, but it will prefer orbits in a thin plane where the forces balance most cleanly. That is the birth plan of disks. Protoplanetary disks, spiral galaxy disks, accretion disks around black holes. The same rule, different scales. You might wonder, if angular momentum is conserved, how can a star or a black hole change its spin? The trick is that conserved means you need an isolated system. The universe is not polite about isolation. Magnetic fields, turbulence, pressure waves, and gravity from nearby structures all provide ways to move angular momentum from one place to another without destroying it. In a newborn star system, magnetic fields act like long, invisible brake lines. Gas in the inner disk threads those fields, and as it tries to turn, the fields link it to slower moving material farther out. The result is a torque, a twist, that moves angular momentum outward and lets inner gas fall into the forming star. That is how a star can form at all. Without this brake, the rotation would support the gas so well that collapse would stall. So the law is intact, but the disk is the courier. It ferries angular momentum outward to pay the bill that gravity presents at the center. When you get to galaxies, the same rules for keeping the books still apply. There is a total spin budget that both the dark matter ring and the gas inside it share. That budget is changed by interactions and torques. It's like a conveyor belt pulling angular momentum from the inner parts of a disk galaxy and putting it in the outer disk and halo. Stars that are close to resonances trade energy and rotational momentum with the pattern. This lets the bar get bigger and the mass inside it get smaller. All of this doesn't go against conservation. It's just a family accounting activity where the totals are the same before and after, even though the pieces move a lot. Extremes are also explained by the same rule. A star's radius shrinks by tens of thousands of times when its core crashes in a supernova. The piece can spin hundreds of times per second to keep its rotary motion. A millisecond pulsar is a neutron star the size of a city that spins faster than a home blender. If it takes in matter from a partner, the gas that falls in gives the pulsar more rotational momentum, which speeds it up even more. Again, conservation is not a chain, it is a bookkeeping tool, and new money coming in helps keep things in balance. Close to black holes, rotation takes on a relativistic twist. A spinning black hole drags space-time around with it, and disks that feed it must negotiate that whirl. If gas falls in on a tilted plane, viscous and wave torques inside the disk can realign the inner regions with the black hole's equator, while sending the mismatch outward, exporting angular momentum through warps. The power in some of the brightest jets in the universe may come partly from tapping the black hole's spin energy itself through magnetic fields. Even there, conservation holds. The jet and radiation carry away angular momentum, the hole spins down, and the books balance. There are also strict rules for conservation. Sunlight has the Yorp effect, which makes small rocks spin up. This happens because the heating and re-radiation are not even, and they work like a tiny rocket. Over time, that torque can make an asteroid spin so fast that loose rock on its surface comes off. The body can lose mass or split into two separate parts if it doesn't stick together well. The safest spin rate varies on the body's size, form, and internal strength, but the basic idea is the same. If you add rotational momentum to a body without changing its ability to hold itself together, rotation will eventually be stronger than gravity and cohesion. Nature takes the record seriously, but that doesn't mean it will be stable. Tidal torque theory. Galaxies used to look like bumpy patches in a universe that was mostly flat in the beginning. At first, those spots, called proto-halos, didn't spin very fast. They got their rotation from their surroundings in a simple way. Mass concentrations close by pulled on them haphazardly, and for long enough to twist them up. That's the idea behind tidal torque. Just picture a blob of matter that is slightly triaxial sitting in a sea of other blobs. The nearby gravity doesn't pull in all directions evenly. It pulls in different directions, stretching one axis and compressing another. The blob shape isn't exactly aligned with the stretch, so it also twists it. After a short time, the twist is very small, but it builds up over millions of years as the patch continues to grow with the world. The proto-halo spin vector comes from the interaction between two tensors. The inertia tensor, which shows how mass is distributed inside the patch, and the tidal shear tensor, which shows how the external gravitational field changes across it. This idea can be written clearly when density contrasts are small. The torques would cancel each other out, and no spin would grow if these two were perfectly lined up. What makes it work is misalignment. There are small primal jitters that make sure the orientation is off, so almost every patch gets some torque. As the cosmic scale factor rises, so does the torque. This means that the rotational momentum builds up until the patch stops expanding, slows down, and turns around under its own gravity. As we get closer to that turnaround, the linear model breaks, collapse speeds up, and spin growth changes. This picture makes several crisp predictions. First, most halos should end up with a modest dimensionless spin. Not zero, not huge, just enough that rotation matters, but doesn't dominate gravity. Second, the direction of that spin isn't random. It correlates with the geometry of the large-scale structure. Filaments, walls, and nodes of the cosmic web feed matter along preferred routes, and the same tidal field that sculpts that skeleton also torques the halos embedded in it. In simulations, lower mass halos tend to have spins aligned more parallel to their filament, while higher mass halos, built by anisotropic infall and mergers, tend to flip towards perpendicular. Third, the bulk of the linear theory spin-up happens before collapse finishes. Afterward, mergers and flows continue to modify spin. But the orderly tidal story gives way to a more chaotic ledger. It helps to visualize a proto-halo as a pebble in a river. The river is the tidal field from a larger scale structure. If the pebble were a perfect sphere, the river would push evenly and there'd be little net twist. But real pebbles are lopsided. The river grabs the long side, the pressure differs across the shape, and a torque appears. Replace the water with gravity, the pebble with a triaxial overdensity, and the outcome is the same. A tiny, persistent twist that builds a meaningful spin by the time the object separates from the Hubble flow. As matter flows in along filaments, it brings with it its own angular momentum budget. The way these streams join can either make the halo's spin stronger or weaker. Depending on the impact parameter and circular sense, mergers can either add or take away. A big merger going backwards can mess up the order of spinning and make a system puff up into a shape that can support more dispersion. A series of smaller mergers going forwards can spin up a disk. It's still possible to remember the early tide field. It is still possible to find coherent connections between galactic spins and nearby filaments. This is especially true in young, low-mass systems that haven't been changed by violent events. Tidal torque theory also sets the stage for what baryons, the gas that will eventually make stars, can do once they cool. The dark halo stores most of the angular momentum early. As gas falls in, it roughly inherits the halo's spin direction and magnitude, then redistributes that angular momentum through shocks, turbulence, and magnetic stresses to settle into a centrifugal disk. If the halo's early torque was weak, the disk will be compact and rotate quickly. If stronger, the disk will be more extended at a given mass. This is why the initial spin matters for observable sizes and rotation speeds. It is not the whole story. Feedback, bars, and misaligned accretion can rewrite local details, but the first draft is written by those quiet early torques. Halo spin parameter. Astronomers like easy numbers that can explain a lot about physics. The halo spin parameter is the most important number for cosmic spinning. It tells you how important the spin of a dark matter cloud is compared to its gravity. Rotation is only important if the number is very small. If the number is large, rotation forms the structure. In other words, the famous version, which was first used by Peebles, is this. Multiply the halo's total rotational momentum by the square root of its total energy value, and then divide that number by the gravitational constant times the halo's mass raised to the power of 5. Take your time reading that. You're looking at how much the circle twists and how tightly gravity holds it together. The result is a number with no units, generally a few percent. Typical values cluster around a few hundredths. In large simulations, the distribution looks log normal with a median near 3% and a broad spread. That modest number is exactly what you would expect from tidal torque theory. Early gravitational nudges give you rotation that is noticeable but not dominant. Why is this little number so useful? Because at fixed mass and concentration, it sketches the size and speed of the galaxy that can form inside. Higher spin halos tend to host more extended disks. Lower spin halos tend to produce compact, fast-rotating systems if gas can cool efficiently. The original meaning asks for the total energy of a circle, which is hard to figure out in systems that are messy and changing. A cousin of this is often used in emulators. It is sometimes called the Bullock spin parameter. In other words, it is the halo's specific angular momentum, which is its angular momentum per unit mass, divided by the sum of the virial radius and the circle velocity at that radius, along with a factor of about 1 over the square root of 2 to make things equal. It's like how spinny per unit mass compared to the halo's natural spin, which is set by its size and speed. This version is more like the old one and is easy to figure out from snapshots. Once you have a spin parameter for a halo, you can make zeroth order predictions. Suppose gas cools and settles without losing much of its angular momentum. Then the characteristic radius of the disk scales with the halo's spin times its virial radius. Double the spin, double the disk size, roughly speaking. The rotation speed of the disk at a given radius will then reflect the balance between the dark halo's gravity and the disk's self-gravity. This is why the spin parameter shows up in semi-analytic galaxy models. Feed in a halo mass, concentration, and spin. Out comes an estimate of disk size, surface density, and rotation curve. Gas doesn't just move inward. When it shocks, it turns into stars, explodes as supernovae, and sometimes it is pushed back out by feedback from stars or an active core. All of these things can change the direction of rotational motion. Angle momentum moves from the inner parts of the disk to the outer disk and into the dark halo through bars and spiral patterns inside the disk. Gas buildup that isn't lined upright can tilt or twist a disk, or even make parts that spin in opposite directions. Even so, the initial spin's marks can still be seen when you average over many computers. The known relationship between angular momentum and star mass, as well as the relationship between disk size and halo size, fits with what the spin parameter says, with a small amount of angular momentum loss added in. The spin parameter also helps interpret outliers. Ultra-diffuse galaxies with large sizes for their mass can live in higher spin halos, stretching their stars and gas over larger radii. Compact, high-surface density disks could come from lower spin halos, or from halos where early gas lost angular momentum through torques and outflows. Dwarfs, being more easily stirred by feedback, often have more complicated relationships. But the baseline still matters. Start with a higher spin budget, and you have more room to keep material at large radii. Spin alignments with the cosmic web. Galaxies don't grow by themselves. They grow on supports. The structure you see there is the cosmic web, a web of filaments, walls, and nodes where gravity has pushed matter into long rivers that feed huge crossings. Tidal torques can change the early spin budget. The web tells matter which way to move, and that direction guidance leaves a mark on the way galaxies spin. It's easy to picture the idea. Picture a small country road that leads to a roundabout. Since most cars come in from the road, the roundabout's flow tends to match that way of getting there. If you swap out cars for dark matter and gas, you get the idea behind spin orientations. Begin with the filaments. They are like roads where halos build up most of their mass after turning around. Low-mass halos that have been through fewer violent events tend to gain rotational momentum from the steady flow of matter coming in. Most of the time, their spins are found to be more parallel to the axis of the thread. To put it another way, their plates move back and forth like wheels along the thread. The story changes as halos get bigger and merge into bigger ones. The shape of the filament determines the paths of approaching subhalos, and big hits that are not in the middle can change the net spin. For big halos, spins tend to point across the thread instead of along it, which is called vertical alignment. Simulations show that this mass-dependent flip will happen, and it does naturally happen when smooth flow gives way to merger-driven rewriting. Walls add another layer. Picture a sheet where two voids meet. Matter flows within the plane of the wall toward nearby filaments etched into that sheet. Halos embedded in walls feel a tidal field that stretches them in plane and compresses them out of plane. The resulting torques tend to align spins within the wall, usually perpendicular to the wall normal. Again, the precise alignment depends on mass and history, but the directional memory is there because the same large-scale gradients that guide the flow also supplied the early twists. Observationally, you never measure the full three-dimensional spin of a galaxy directly. You infer orientation from its projected shape, rotation field, or both, then compare that with a reconstructed map of the local web. Despite those hurdles, surveys have begun to see the same hints that simulations flag. Disk galaxies in thin filaments show mild preferences for their spin to lie along the filament, while more massive early-type systems in thicker filaments or near nodes show weakened or flipped alignments. The signals are subtle and need huge samples to rise above noise, but they point in the same direction as the theory. There are strong connections, and the fact that they connect scales makes them even more so. There is a thread millions of light-years long that helps a spiral galaxy that is only a few tens of thousands of light-years wide line up. We can test models of how structures are made on that bridge. As the properties of dark matter, the rate of growth, or the amount of feedback that can move gas around and mess up alignment patterns change, so do the patterns that were expected. As more of the sky is mapped with better mechanics, these patterns can be used to learn more about the past. Alignments also carry practical consequences for how galaxies evolve. Gas does not always arrive neatly. If fresh gas flows in a direction tilted relative to an existing disk, the mismatch can warp the outer disk, tilt the inner one over time, or even lay down a polar ring. Bars and spirals inside the disk will work to redistribute angular momentum and smooth out small misalignments. but strong, sustained misaligned inflow can leave lasting marks. The outer gaseous disk may keep the memory of the filament direction long after the stars inside have heated and blurred that memory. Cold flow accretion feeds disks. Galaxies are not closed bowls that only mix up what's already there. Instead, they are open systems that are linked to the rest of the universe by long, thin streams of gas. These streams are cold flows because the gas doesn't get shocked and heated up to the halo's hot, almost viral temperature. Instead, it stays cool and dense as it dives in along filaments. The most important thing to know about spin is that these flows don't just happen. They carry the angular momentum set by the same large-scale tides that shaped the halo. This means that they provide fuel and a direction cue that helps draw the disk that forms. Whether gas arrives cold or hot depends strongly on halo mass and cosmic time. In lower mass halos and at early times, the gas can radiate away the heat from compression fast enough that a stable global accretion shock never forms. The flow threads the halo like a pipeline, reaching the inner region still cool, dense, and rotating with the angular momentum it picked up en route. In more massive halos, especially at later times, a standing shock can heat infalling gas to millions of degrees. Even then, narrow, denser streams may punch through that hot atmosphere and remain relatively cool. Either way, the filament geometry matters. Accretion is not a spherical drizzle, but a set of preferred lanes that preserve coherence over large distances. Cold flows do more than refill the tank. They help set the size and spin of the disk that forms. Think of specific angular momentum per unit mass, as the key currency. If the inflow carries high specific angular momentum, the disk that forms is more extended for a given mass, because gas must orbit farther out to balance the angular momentum budget while settling. If the inflow carries low specific angular momentum, the disk can be more compact and rotate faster at small radii. This is why simulations that track the spin content of the inflow can predict, at least in broad strokes, the size-mass trends of galaxy populations. The flow's direction is also important. If new gas comes in and lines up with the disk that's already there, it builds up the outer areas easily, making the galaxy bigger from the inside out. If it comes tilted, it can bend the outer disk, tilt the inner disk over time, or even lay down parts that are stacked in each other in different ways. If misaligned input continues for a long time, it can make a polar ring, a beautiful structure where gas orbits almost perpendicular to the main star disk. Torques inside the disk, such as those caused by spiral patterns, bars, and turbulence, will always work to shift rotational momentum and gradually fix the mismatch. However, the marks of the inflow direction may stay, especially near the edges. Cold flows also change stability. A fresh supply of cool gas lowers the velocity dispersion of the disk and raises the surface density. Disk stability is often summarized by a single parameter, traditionally called Q. Narrated in words, Q compares the tendency of gravity to clump the disk with the opposing tendency of rotation and internal motions to smear it out. When Q drops below about 1, gravity wins locally, and the disk fragments into giant star-forming clumps. High inflow rates at early times push Q downward, so disks at high redshift are often clumpy, thick, and vigorously forming stars. The clumps themselves migrate inward under torques and dynamical friction, carrying mass and angular momentum with them and helping to build central bulges. Another way to see the role of cold flows is through compaction events. If the inflow briefly brings in lower specific angular momentum gas, or if internal torques funnel gas inward, the central surface density can spike. Star formation surges, winds blow, and the disk can temporarily become more compact. Afterward, if high specific angular momentum gas resumes feeding the system, the galaxy can regrow a more extended disk. This push-pull cycle paints a path across size and surface density that many observed galaxies seem to follow, with outer disks often younger and more metal-poor, consistent with later cold inflow. In this story, the hot halo doesn't do anything. It can be a container that slowly cools and drips gas onto the disk over a long period of time, even when there is a world shock. What the cooling gas's rotational momentum shows is where and how it last mixed with the halo as well as the filaments that fed it. As satellites curve in along filaments, they give both mass and rotational momentum. The gas that they remove can join the disk, sometimes with a clear direction that creates warps and outer rings. There are three main ways that the galaxy's spin record is made up: direct cold streams, cooling from the hot atmosphere, and input from satellites. Disk collapse and centrifugal support. If you give gravity a cloud that is moving, it will try to pull everything into the middle. Rotation won't work. It leads to a truce, a thin, flat disk where the pull inward is matched by the tendency of moving matter to keep going around on the sides. The idea is like swinging a bucket of water back and forth. The faster you swing, the more water stays out. This stay-out effect is the centrifugal side of the balance in galaxies and protoplanetary systems. It sets the radius where gas can circle without falling in. Gas is a good mediator because it can lose energy without turning around much. As a cloud falls in, it shocks, heats, and moves around randomly. It moves to a lower orbit as it loses energy. However, the gas keeps enough turning power to circle at the radius where its spin fits a stable orbit. This is because angular momentum is mostly maintained. Unless you do that with a lot of boxes, you won't get a ball, you'll get a plate. The gas then settles down and turns into stars. The stars' birthplaces give them a flat shape and paths that are very close to circles. Why thin instead of puffy? Look vertically. Gravity from the disk and halo pulls material toward the midplane. Gas pressure and random motions try to puff it up. Where those two effects balance, you get a characteristic thickness called the scale height. Colder, calmer gas makes a smaller pressure push, so it settles into a thinner layer. Hotter, more turbulent gas pushes harder and sits thicker. That is why spiral galaxies often show razor-thin dust lanes at the very center of their disks. Cool gas, low turbulence, strong gravity, tight sandwich. Disks are not uniform. The inner regions feel stronger gravity, so at a given level of turbulence they can be thinner. The outskirts feel weaker pull and can flare, bending upward into a gentle bowl. Fresh, misaligned accretion can also warp the outer layers, tilting the gas relative to the inner stars. Even so, the same balance rules apply locally. Where gravity is stronger and random motions are smaller, the disk is thinner. Kinematic thinness is the second type. Most orbits are almost circular in the plane of the disk. That means rotation is more important than random motion. Rotation curves, which are graphs of orbital speed versus radius, show how gravity and spin work together. In many spirals, the speed stays pretty steady from the bright center circle out to the large arcs. That means the mass that makes gravity work isn't just in the stars you can see. A dark halo helps carry the weight so gas and stars can circle quickly without falling in on themselves. Again, you don't need math to understand this. Just a steady move sideways that opposes the pull inward. Time makes things thicker. There are no collisions between stars, and once they are born, they don't give off random motion like gas does. When they meet big molecular clouds, spiral arms or bars, they move their orbits up and down a little, which slowly warms the star disk. On a bigger scale, minor unions and satellite passes do the same thing. This is the reason why many galaxies have a two-layer structure, a thin ring of gas and young stars, and a thicker, older part with paths that are more rounded. The stars remember every bump in the gas because it cools down. The same logic plays out on smaller scales around young stars. A protoplanetary disk is razor-thin near the star, where gravity is strong and the gas is cool, and thicker farther out where gravity weakens. Small dust grains settle toward the midplane, where collisions and sticking begin building planetesimals. Because the gas keeps its angular momentum while losing energy, planets form in a flat, rotating sheet. Later, gravitational nudges can tilt or warp things, but the default is a thin plane. Stability keeps disks honest. If a patch of disk gets too dense and too calm, Self-gravity can overwhelm the stabilizing effects of rotation and internal motion. Then it fragments into clumps and spawns stars. Astronomers roll that tendency into a single yardstick, often called the Q parameter. Low Q means easy to collapse. High Q means hard to collapse. Inflow of cool gas lowers Q and thick, clumpy disks appear, common in the early universe when supply lines were rich. Feedback from star formation and central activity raises Q, heating and stirring the disk, which then thickens until balance returns. Spiral density waves move momentum. It may look like spiral arms are made of matter, but they act more like traffic waves on a highway. The cars are like stars and gas clouds, and the traffic jam is the arm. Each star or cloud goes into the arm, slows down a bit, gets brighter if it turns into a star, and then leaves the arm on the other side. The design can stay the same, even if particles move around. We can now solve a long-standing problem with this wave picture. Within a few turns, shear would make the arms too tight if they were made of a set material. Since they are waves, they can stay at a nearly constant pitch for billions of years. This is because the disk's self-gravity, spinning, and asymmetries like bars or partners hold them up. The magic of spiral density waves is their ability to move angular momentum without shredding the disk. Inside a special radius, the corrotation radius, stars and gas orbit faster than the pattern. Outside, they orbit slower. On the inner side, the wave exerts a backward tug, taking angular momentum from the material and letting it drift inward slightly. On the outer side, it gives a forward shove, adding angular momentum and nudging material outward. This gentle conveyor belt smooths the disk, builds rings near resonances, and helps keep the overall structure stable. The wayfinding is done by resonances. The best place for the exchange of energy and rotational momentum is where the star's natural epicyclic wiggle lines up with the pattern's force. At the inner and outer Lindblad resonances, gas can build up into rings. As you get closer to corrotation, gas stays in the arm longer, which helps stars form. For any of these reasons, the disk doesn't need to be weak. In fact, waves stop sharp pileups that would break apart out of control by spreading rotational momentum out slowly. Gas responds more vividly than stars because it can shock and cool. As a gas parcel enters an arm, it faces a compressed higher pressure region and slows. The compression boosts density, triggers cloud collapse, and ignites star formation along the arm's leading edge. Hot young stars light the spiral like runway markers, and supernova feedback stirs the interarm regions, helping reset the medium for the next pass. The newborn clusters drift downstream, so the sequence along an arm, dust lane, H2 regions, young blue clusters, acts like a clock that confirms the wave picture. It's rare for spiral designs to appear out of nowhere. They can be spread out or made stronger by bars, tidal impacts, or even uneven dark halos. Gas is pushed in by a bar, which gives rotational motion to the outer disk and halo. The ends of the bar often connect to two grand-designed spiral arms, which keep the wave going. A close pass from a neighboring galaxy can set off a strong two-armed pattern that lasts for a long time after the invader moves on. M51 is a famous example of this. Even in disks that aren't as noisy, swing amplification, a feedback between leading and following disturbances under shear, can make small noise bigger into a structure with many arms that can be seen. The effect builds up over time and is subtle but strong. Waves move a small amount of the disk's axial momentum from the inside to the outside, making the outer disk thicker and helping the inner areas move gas toward the center. This can help rings of stars form near inner resonances or a center bulge grow. The slow and global nature of the process makes it possible for secular evolution, which means change that is driven by internal dynamics instead of violent mergers. This long dance between waves and circles is what gives many late-type spirals their neat rings, slowly rising rotation curves, and groups of stars of different ages. Spiral waves also communicate with the dark halo. Stars near resonances can transfer angular momentum to halo particles whose orbital frequencies match the pattern, allowing the wave to persist longer than it would in a purely stellar disk. In return, the halo's response can either damp or sustain the pattern depending on its distribution and velocity structure. This exchange is another reason disks evolve without breaking conservation laws. Nothing disappears. It just migrates between components. Predictability is a useful benefit of the wave structure. You can find corrotation and the key resonances if you can guess the pattern speed, which is how fast the spiral turns as a shape. Near those edges, look for rings and holes. Find the differences between the dust lanes and the young groups to figure out how fast the gas is moving around in relation to the pattern. In barred spirals, there will be an inner ring that goes around the bar and an outer ring that goes further away. Each ring will trace a key vibration. With these signals, scientists can make maps of the galaxy's unseen dynamical skeleton that lies beneath its visible arms. Bars are angular momentum engines. A stellar bar is a self-organized lever arm made up of billions of stars moving in long orbits that line up to make what looks like a hard bridge across a disk. It's not a solid bar. It's a pattern that spins as a single unit at a set speed. The bar is not a circle, so it pulls on stars, gas, and even the dark matter ring around them in a steady way. Because of these torques, angular momentum moves from the inner disk to the outer disk and ring. This changes the shape of the galaxy without a single crash. Imagine a moving belt on a factory floor. The material near the middle doesn't spin and moves inward. The material on the edges spins and spreads more. Gas reveals the process vividly. As the bar turns, its gravity pulls gas off circular paths into offset lanes that run along the bar's leading edges. Shocks in those lanes compress the gas, lighting up dust and star-forming regions. The shocks also bleed energy from the gas, but leave much of its angular momentum budget to be traded by the bar's torque. The net effect is inward drift along the bar until the gas reaches radii, where the torques weaken or change sign. There, gas piles into bright inner rings or pours deeper toward the very center, feeding bursts of star formation and, in some galaxies, a hungry black hole. Over many bar rotations, this conveyor can grow a dense, disky pseudo-bulge built by secular processes rather than violent mergers. Resonances are the bar's signposts and control points. At the special radius where stars and gas orbit with the same period as the bar's rotation, exchanges are gentle and material lingers. This is corrotation. Farther in and farther out live the inner and outer resonances where natural orbital wiggles match the bar's forcing. Near these radii, torques are especially efficient. Gas tends to settle into rings close to the inner resonance or at the bar's ends, near corrotation, and into larger outer rings beyond. Observers use these rings as dynamical landmarks. Measure a pattern speed, look for a ring, and you can mark where the bar's influence switches gears. Bars rarely act alone. Their ends often launch two graceful spiral arms. The spirals carry the bar's torque farther into the disk, continuing the inside-out transfer of angular momentum. The bar also torques to the dark halo. Orbits in the halo that precess at just the right rates can absorb angular momentum from the bar, letting the pattern persist and even grow. In return, this exchange tends to slow the bar's rotation slightly over cosmic time. How much it slows depends on how dense and responsive the central halo is. A more massive, more reactive halo is a larger sponge for angular momentum, and the bar pays by spinning down. Bars change, sometimes in big ways. They can get stronger and longer as they move their angular momentum outwards. When gas is put into the center, it makes it denser, which can either support the bar or, if it's too dense, weaken it by messing up the circles that keep the bar together. Another important step is vertical bending. After some time, the bar may become unsteady when it's not in the plane. It may bend up and down like a slightly bent ruler. From the side, it looks like a boxy or peanut-shaped bulge. That thicker structure is a record of rotational momentum trades that happened in the past, like a fossil of bar dynamics. What triggers a bar? A massive, relatively cool, rotationally supported disk is prone to non-axisymmetric instabilities. In plain terms, if the disk is too self-gravitating and not too hot, it prefers to organize into a bar. Interactions can hasten the outcome. A close flyby or tidal nudge can seed the pattern, which the disk then amplifies. Once present, the bar is remarkably persistent. Even when gas accretion or feedback events rattle the disk, the bar often reforms because the underlying orbital skeleton remains. Chemical and mechanical marks are left behind by bars. By pushing gas inward, they make the metallicity gradient steeper in the middle and can smooth it farther out as the disk spreads out. They also change the way stars move. Orbits that are caught by the bar change from nearly spherical to long families that support the bar's shape. These changes affect how the bridge looks and moves. This galaxy's bright inner ring, dust lanes that curve into a bar, and boxy center bulge all show the same thing. There is torque here, transport there, and growth above and below. Bars are important to secular evolution, the slow change that galaxies go through because of forces inside them. They can make fake bulges, feed nuclear rings where stars form bands of light, and control the growth of the center black hole by changing the flow of gas. None of this breaks rules about protecting wildlife. The bar only moves the entries in the ledger. The inner disk gives angular momentum. The outer disk and halo receive it, and the center gets mass in return. Lindblad resonances shape rings. Galactic circles are like busy roads, and resonances are like the roundabouts where the flow of traffic changes. When the natural rhythm of an orbital meets the rhythm of a spinning pattern like a bar or spiral, this is called a resonance. When a star is in a near-circular orbit, it does two things at once. It goes around the center and slowly moves in and out like a small epicycle. When the pattern's spin rate lines up with that in and out wiggle, this is called the inner Lindblad resonance. On the inner side of the pattern, the star feels a push at the same period every lap. From the outside, the mirror box on the far side is the Lindblad resonance. The kicks add up because they come at the right time, and angular momentum is traded well. The rings and holes we see are made by matter piling up or emptying out these radii. Corrotation sits between the two Lindblad resonances. That is the radius where the material orbits at the same angular speed as the pattern itself. There, stars and gas linger in the bar or spiral frame, so torques average to nearly zero, and crowding can occur along stable families of orbits. Inside corrotation, the pattern overtakes the material, and the net torque tends to be negative, drawing angular momentum outward and letting material drift inward a little. Outside corrotation, the opposite happens. The pattern is slower than the material, the net torque is positive, and matter is nudged outward. Lindblad resonances mark the transition zones where these exchanges peak. Gas advertises resonances more clearly than stars. Being collisional and able to cool, gas responds to the timed nudges by shocking, compressing, and settling. Near the inner Lindblad resonance, gas streams along the bar's dust lanes until the torque weakens and switches sign. It slows, piles up, and forms a bright star-forming inner ring that often hugs the bar. Near the outer Lindblad resonance, spiral arms can end in arcs that loop into a graceful outer ring or pseudo-ring. In barred galaxies, the catalogue of ring types, nuclear rings close to the center, inner rings encircling the bar, outer rings beyond, maps neatly onto resonance locations. Astronomers use the sizes and shapes of these rings to back out the bar's pattern speed, match the observed ring radius to the expected resonance radius, and the bar's rotation rate falls out. Under the hood, the key is how families of stable orbits change with radius. Inside the inner resonance, the most stable elongated orbits tend to align perpendicular to the bar. Between the inner resonance and corrotation, they flip to align with the bar. Gas trying to follow those orbits runs into itself at the transition, shocks and loses energy, which helps it gather into a ring precisely where the orbital families hang off. Stars, being collisionless, do not shock, but they can be trapped by these families over long times, building stellar rings that echo the gas structure. The place where spiral arms do best is also set by Lindblad resonances. A two-armed spiral with a steady pattern speed often goes from the ends of the bars to the outer Lindblad resonance. It fades as the resonance support weakens. As the pattern speed changes, multi-armed or flocculent patterns tend to be more transient and can change their effective resonances. However, the same rules still apply. Arms are loudest when the disk can easily hand over rotational momentum and quietest when the coupling is weak or out of tune. Because resonances are timing devices, anything that changes the timing will move them. If a bar slows as it trades angular momentum to the outer disk and halo, corrotation and the Lindblad radii creep outward. The inner ring may grow, the outer ring may migrate, and the gap between them may refill or deepen depending on gas supply. Conversely, if fresh gas inflow spins up the inner disk slightly and the effective pattern speed increases, the resonances can inch inward. Observationally, comparing ring sizes in bars of different strengths and host masses offers a way to track this secular evolution. Also, resonances can cross over. It is possible for a galaxy to have both a fast bar and a slower spiral, each with a different pattern speed. It is possible for the joint force to thicken or thin bands, strengthen or break arms, or cause bursts of star formation when one resonance is close to another resonance. In the worst situations, resonance overlap can stir the stars even more, which can heat the disk and make it puff up. Even so, the clues are still there. Rings close to the inner regions point to the inner resonance, rings at the ends of the bars point to corrotation, and rings on the outside point to the outer resonance. The same thoughts are smaller. Some planets move around in protoplanetary rings, which is what they're called. Its gravity makes the gas around it have inner and outer Lindblad resonances. It moves angular momentum around and fills in a space around the planet's rotation with gas. What's inside the circle tends to lose angular momentum and move toward the center, while what's outside gets it and moves away. This makes a ring gap system that looks a lot like the bar ring structure of galaxies, but much smaller. Similar ideas explain how shepherd moons in Saturn's rings work. Resonant tugs keep edges sharp and lanes open. Warps, tilts, and polar rings. Even though galactic disks look like they should stay flat, many of them bend, twist, and even form second disks that grow at right angles to the first. These forms aren't just for looks. They show how new gas gets in and how rotational momentum is moved around. The clearest example is a normal S-shaped warp in the hydrogen layer on the outside of a spiral galaxy. There is a flat surface inside the star disk. The gas outside the disk bends above the flat surface on one side and below it on the other, like a record left in the sun. This pattern shows that the outer gas is trying to circle in a plane that is tilted relative to the inner disk, but it hasn't quite lined up yet. Where does the tilt come from? Most often, from misaligned accretion. Gas that falls in along a filament does not always share the exact orientation of the existing disk. If the inflow's angular momentum vector is slightly off, the outermost layers absorb that mismatch first. Gravity from the inner disk and halo then exerts torques that try to bring the newcomer into line. The result is a warp transition region that slowly precesses and, over many rotations, tends to align if the misaligned supply turns off. Keep the tilted supply coming, and the warp persists, sometimes for billions of years. Satellites and minor mergers add another pathway. A small companion dragged toward the disk sheds gas through tides and ram pressure. That stripped gas can wrap into the host on an inclined plane, seeding a warp, or, if the angle is large and the inflow coherent, building a striking polar ring. Polar ring galaxies wear a luminous hoop, or full secondary disk, orbiting nearly 90 degrees to the main stellar disk. The ring often contains gas and young stars, rotates cleanly, and can be surprisingly long-lived. It forms when a steady supply of inclined material settles into its own, dynamically supported plane, rather than being immediately torqued flat. Why doesn't gravity just flatten everything quickly? because alignment is a tug-of-war between internal torques and the inertia of the incoming angular momentum. Disks communicate their preferred plane through gravitational coupling, and in gas through pressure and magnetic stresses. But the outer parts are loosely bound and feel weaker restoring forces, so they are easily tipped. If the halo itself is slightly triaxial, or its figure tumbles slowly, it can add a gentle, steady torque that maintains a warp. In many systems, the warp aligns with the local filament direction, hinting that the large-scale flow keeps setting the boundary conditions while the inner disk negotiates. Warps come with kinematic clues. In a tilted outer layer, the line of nodes, the curve where the warped plane crosses the inner plane, twists with radius. That twist shows up in velocity maps as a changing orientation of the rotation field, even when the rotation speed stays smooth. Radio observations of atomic hydrogen excel here. They trace orbits well beyond the optical edge, revealing graceful, twisted velocity fields that map the warp in 3 dimensions. In some galaxies, the warp bends only one way, an integral sine warp. In others, it can be lopsided, with one side flared more than the other, betraying an asymmetric inflow or a recent nudge. Polar rings provide unique leverage on the unseen mass, because one stellar component orbits in the equatorial plane, and another in a perpendicular plane. Their combined motions sample the galaxy's gravitational potential in 2 independent directions. If the dark halo were strongly flattened along the main disk, the polar ring's rotation would betray it. If the halo is rounder, the ring's dynamics say so. Observers use this 2-axis test to infer halo shapes, one of the few clean, dynamical probes available beyond the inner regions. Nested objects can also be made by growth that is not lined up right. When gas comes in at one angle, it may make an upper layer that is twisted. After some time, gas that is slightly tilted can settle inside, making an inner disk or ring that is tilted compared to the main disk. In the worst situations, the inner part turns the opposite direction. These kinematically separated cores are perfect for fueling that happens in spurts and isn't aligned correctly. First give spin one way, then turn the flow off. Over time, what happens depends on how much supply and waste there is. If movement that isn't aligned stops, viscous and gravitational forces in the gas will work to align it. The warp slows down, the ring spreads out, and it slowly leans toward the main plane. This makes the whole system more symmetrical. As long as the supply keeps going, the outer warp can stay in place for a while, with new gas constantly adding to the bent layer. Stars form in wavy areas, and the geometry freezes in. This leaves behind new stellar arcs that keep the shape off-center long after the gas flattens out. Counter-rotation and decoupled cores. A star doesn't always just move, sometimes it flips. You see that the gas and stars in the main disk are spinning in one direction. Then you see a second part that is either gas or stars spinning in the opposite direction. That is spinning against itself. If you make the difference even bigger, you'll find a kinematically disconnected core. This is an inner island that spins at a very different speed or spin axis from the outer galaxy. You can't call these quirks. They're just the way galaxies take in new stuff and trade angular momentum after the fact. The cleanest path to counter-rotation is external accretion. A gas-poor disk or S0 galaxy can sweep up gas from a passing cloud or a small companion on a retrograde orbit. The captured gas settles into orbits opposite the old stellar disk because that is how the incoming angular momentum points. If the inflow persists, the retrograde gas forms stars, building a young, thin, counter-rotating stellar disk embedded in an older, thicker prograde one. You can see the timeline in the stellar ages. The retrograde disk is bluer and younger. The host is redder and older. Stars and gas with opposite spin are given away by a small merger on a backward track. A big collision between spiral galaxies that aren't lined up right can mess up the outer galaxy, while the center few kiloparsecs are controlled by the dense core of one parent galaxy, or by a new, compact disk from gas flowing in and out. The core is now separate from the outer body, and can spin around a different axis or even at right angles to it. Large cores with their own spin histories are common in boxy, slow-rotating ellipticals. These cores are fossils of big mergers that didn't have a lot of gas. Small, disc-shaped cores in faster rotators often point to a later event that was full of gas and remade the center. Gas physics decides who wins the plane. Gas is collisional and dissipative. It can radiate energy, settle, and align if torqued hard enough. Stars are collisionless. Once in a family of orbits, they keep memory. So a typical sequence goes like this. Retrograde gas arrives and orbits backward. Shocks and torques compress it, ignite star formation, and over time either feed the very center or build a thin, counter-rotating disk. If new prograde gas later arrives in bulk, the two gas streams can cancel net angular momentum and plunge inward, feeding a starburst or an active nucleus. If the retrograde supply continues instead, the counter-rotating layer thickens and survives. These setups are dynamically delicate. Two streams moving through each other with opposite rotation invite instabilities. In gas, the shear where the layers meet can trigger turbulence and rings. In stars, overlapping families of orbits can heat the disk and create thickened zones. Yet many counter-rotating systems are long-lived, which tells you the mass fractions are moderate, the layers are vertically separated, or the orbits are organized by resonances that reduce direct crossflow. Observationally, counter-rotation announces itself in several ways. Long-slit spectra show double-peaked absorption or emission lines near the midplane, one peak from each spinning component. Integral field maps reveal velocity fields that flip sign between gas and stars, or twist sharply in the center where a decoupled core takes over. Many galaxies show a sigma drop, a dip in stellar velocity dispersion in the inner kiloparsec, when a cold, rapidly rotating central disk dilutes the hotter background. Color maps and line strength diagnostics then sort the ages, young stars tracing the retrograde gas, older stars marking the host. Accreted gas from a small metal-poor companion leaves a central disk with lower metallicity than you would expect for its radius, sometimes with enhanced alpha elements if the starburst was brief and intense. Counter-rotating stars built from that gas share the pattern. If the gas came from a stripped spiral instead, metallicities are higher and gradients flatter. In this way, kinematics and chemistry together point back to the source. Counter-rotation matters for black hole fueling and ring building. Oppositely spinning gas layers experience strong torques where they interact. That cancels angular momentum and drives inflow. Nuclear rings, dense star-forming wreaths often found near inner resonances, are common in systems that have recently ingested misaligned gas. The same inflow can spin up or spin down the central black hole, depending on which side dominates and when the accretion arrives, leaving echoes in jet direction or variability. In loose groups with lots of cold gas and slow encounters, misplaced accretion and small mergers happen a lot. This is why S0 galaxies often spin backwards. Disks get dry in rich clusters because of ram pressure stripping and abuse. Decoupled cores in those clusters are more likely to be old merger leftovers than new gas stories. The cosmic web still whispers directions. As satellites fall in along strands, they choose which spin senses are free to be given away. Mergers, flip spins, and quench rotation. Not only do two galaxies add mass to each other, but they also trade, mess up, and sometimes lose rotational momentum. Ordered disk spinning is put to the test by a big merger with masses that are basically the same. If the collision is prograde, which means that the partner disk orbits in the same way as the main disk, then tidal forces can first make spirals and bars bigger, which moves the disk's angular momentum outward and pushes gas toward the center. If the orbit is going backwards or very steeply inclined, the crash will more effectively mix up the paths of the stars, tearing apart the smooth circles that keep the disk small. If either of these things happen, the system can end up much larger and hotter, with pressure support in place of rotational support and only a weak memory of a neat spin. The dance moves begin a long way away. The smaller galaxy is pulled inward by dynamical friction, long before the cores touch. This happens by sending orbital rotational momentum to the background halo and outer disk. Because of the friction, an orbit that used to be wide and fast gets narrower and slower. This means that each pass at the pericenter has less rotational momentum and more time spent under strong waves. Every time they go by, tidal arms form and throw stars and gas outward. This stops the rotational motion in the dark halo and the long tails. In the middle, what's left is thicker and less ordered, ready to compact and burst into stars. Gas is the decisive witness. Being able to shock and cool, it sheds orbital energy quickly during close passages and streams inward along bars and bridges. The inward surge raises central gas density, lights a starburst, and, if a black hole waits at the core, feeds it. The same inflow steals angular momentum from the inner regions, further tilting the balance away from rotation. Once the burst burns through the gas or feedback heats and expels it, the center becomes dynamically hot and less able to regrow a thin disk. In this way, the merger both erases the old spin and cuts off the fuel that would have restored it, 2 steps toward quenching. Whether a remnant keeps any ordered rotation depends on the orbits that survive. Stars in disks move on nearly circular paths. Stars in merger remnants occupy a mix of elongated, tilted, and sometimes boxy paths that do not sum to a clean spin. If the progenitors were gas-poor, the result is often a slow rotator, a spheroidal galaxy with little net rotation and a flat or even twisted velocity field. If they were gas-rich, the gas that survives can settle after the storm and rebuild a central rotating component embedded in a hotter envelope. That is why some merger remnants show a fast spinning inner disk, sometimes even counter-rotating, inside a rounder body. The remnant's kinematics are a ledger of which orbit families won. The total angular momentum of the system is conserved, but its direction can change. A series of inclined encounters can torque the remnant's net spin axis to a new orientation, especially if the outer halo absorbs a large share of the original spin. The center may then rotate around an axis tilted relative to the old disk, or not at all. This reorientation is easier when feedback has puffed up the central mass distribution, making it less stubborn about keeping a fixed plane. In small groups, where relative velocities are modest, mergers are frequent and transformative. There, we see many quenched, dispersion-supported systems, the fossils of past spin erasure. In rich clusters, high speeds make direct mergers rarer, but repeated high-speed flybys and tidal harassment can strip outer disks, heat stellar orbits, and gradually sap rotation even without a clean coalescence. In both settings, streams and shells in stellar halos betray the long settling time of debris, which is where much of the lost angular momentum now lives. There are a few things that make quenching likely after a merger, but it's not a sure thing. First, the center flare burns through gas very quickly, while supernovae and stellar winds heat and stir up what's left. Second, a black hole that is fed can create an active center whose energy is shared with the gas around it, keeping it hot and afloat. Third, the halo has been remade to be more spherical. This creates a steady shock that heats new ice before it can reach the center, cutting off the cold supply lines. A thin disk that is making stars has a hard time growing back without new gas with a high specific rotational momentum. Star formation stops and sputters without cool fuel. Yet mergers do not write only one ending. A gas-rich merger at high redshift can trigger an intense burst. Then, if cold streams resume, the remnant can regrow a large rotating disk around a compact central bulge. In that case, the galaxy's spin comes back, but its structure records the detour, a thickened inner component, perhaps a bar, and an outer disk with younger stars. Alternatively, repeated minor mergers can gradually fatten a disk and tilt its axis without fully destroying rotation, producing a fast rotator with kinematic twists and subtle misalignments. Specific angular momentum tracks mass. A striking pattern can be seen when you line up thousands of galaxies and measure 2 easy things: the mass of their stars and how much rotational momentum they have per unit mass. Disks, spheroids, and everything else fall along tracks that are very close to the power law. This is because specific rotational momentum goes up as star mass goes up. To put it simply, bigger galaxies tend to hold more spin per kilogram, and the shape of that rise relies on the type of galaxy. What you see in a rotation curve or velocity map is linked to where a galaxy is on a universal spin mass chart. This is what makes neat relationships like Tully-Fisher for spirals and its cousins for ellipticals possible. Start with spirals. Their stars move on near-circular orbits in a disk with a characteristic size and a fairly flat rotation curve. Multiply a representative radius by the rotation speed and you get the rough specific angular momentum of the stellar disk. Empirically, that number scales with stellar mass, with a slope close to 2/3 when you write mass as a power and take logarithms. Narrated instead, if you increase the stellar mass by a factor of 8, the specific angular momentum rises by about a factor of 4. The scatter is modest, and late-type galaxies line up along a tight ridge because their ordered rotation stores spin efficiently. Ellipticals tell a complementary story. Their stars are supported more by random motion than by rotation, so the same bookkeeping, now using effective radius and a characteristic velocity dispersion or slow rotation speed, lands them on a parallel track shifted downward. At a given stellar mass, they carry less specific angular momentum than spirals. That offset is a fossil of their histories. Mergers and violent relaxation traded a chunk of ordered spin for pressure support and parked angular momentum in outer halos and tidal debris. Why does the slope hover near 2/3? Because the spin of a galaxy inherits the statistics of its dark halo. In simple halo models, the virial radius grows roughly like the cube root of halo mass, and the circular velocity grows roughly like the 6th root of halo mass. Multiply those two, and you get a specific angular momentum that scales close to mass, raised to 2/3. If baryons kept a fixed fraction of the halo's angular momentum as they cooled and settled, they would trace a similar slope. Real physics complicates this handoff, but not enough to erase the imprint. Feedback, torques, and misaligned accretion broaden the relation without changing its basic tilt. Now connect this to classic observables. The Tully-Fisher relation links a spiral galaxy's luminosity or stellar mass to its flat rotation speed. Brighter disks rotate faster. Combine that with the fact that disk size correlates with mass and halo properties, and you find that specific angular momentum, roughly size times speed, naturally increases with mass. For ellipticals, the Faber-Jackson style links between luminosity, size, and velocity dispersion play the analogous role. But because dispersion does not store angular momentum as efficiently as ordered rotation, the normalization drops. Choices about inclination, thickness, and mass-to-light ratio add to the noise of observations, but they don't hide the physics behind them. When integral field spectroscopy maps the full two-dimensional motion of stars, you can get a clean specific angular momentum that is weighted by brightness and put each galaxy exactly where it belongs. The slow rotators are huddled low, and the disks are grouped along the high-spin line. The mixes are in the middle. It has been found that atomic and molecular rings have even more specific angular momentum than stars of the same mass. This is because they live in cooler, more circular orbits with bigger sizes. There are useful outliers. Ultra-diffuse galaxies with large sizes but modest masses sit high for their mass, consistent with living in higher spin halos or retaining a larger fraction of their halo's angular momentum. Compact high surface density systems sit low, hinting at early angular momentum loss via torques, outflows, or dissipative events that drove gas inward before most stars formed. Dwarfs can swing wide because feedback stirs them strongly, changing both size and rotation support across time. Still, when averaged over many, they trend along the same slope. In dense regions, harassment and gas stripping can lower a disk's specific angular momentum by shrinking its gas reservoir and thickening its stellar motions, pushing it toward the early type track. In the field, steady cold inflow can keep a disk on the high spin ridge, growing size faster than mass. Because the underlying halo spin distribution is broad but centered on a few percent in the dimensionless sense, you should expect a correspondingly broad but structured cloud of points in the spin mass plane. Exactly what surveys find. Baryon dark matter exchange via friction. Bars and disks don't spin in space. They move through a sea of dark matter. That sea moves. When something big moves, it concentrates the particles behind it into a wake that is too thick. The gravitational pull of the wake pulls the mover backwards and gives some of its velocity to the background. The quiet broker exchanges rotational momentum between the halo and the bright matter. This is what dynamical friction looks like in simple terms. Picture a barred galaxy. The bar is a rotating mass excess, so it stirs the halo. Orbits in the halo that precess at the right rate fall into step with the bar's pattern and soak up angular momentum. The bar loses a bit of its spin and can slow, while the halo gains that spin and slightly reorients its inner orbits. You do not need equations to see the direction of travel. A lever pushing on a fluid rings up ripples, and the ripples push back. Over billions of years, that backpush can lengthen the bar, thicken the central stellar distribution into a boxy or peanut shape, and migrate resonances outward as the pattern speed declines. Disks themselves feel the same exchange. A clump of gas or a giant star-forming complex orbits through the halo and raises a wake. The wake pulls back, draining orbital energy and angular momentum and letting the clump sink a little closer to the center. In gas-rich, high-redshift disks, where clumps are massive, this friction-driven sinking helps build central bulges. In today's calmer disks, the effect survives but is gentler, helping smooth mass profiles and feed bars without erasing the disk. Satellites are friction's marquee clients. A dwarf galaxy on an eccentric path through a larger halo leaves a bright breadcrumb trail in phase space. Its wake. With each pass, orbital angular momentum moves to the outer halo and the satellite spirals inward. The outer halo, now with extra angular momentum, puffs and spins slightly faster. The satellite, with less, tightens its orbit and eventually merges. The same physics shrinks the orbit of a supermassive black hole pair after a galaxy merger. Stars and gas clear the first rungs of the ladder, then friction against the dark and stellar background carries the holes toward coalescence, where gravitational waves take over. This conversation isn't just a drag. The knob can also be used to adjust the form and steadiness of the disk. As soon as a bar gives the halo axial momentum, the inner disk can lose some of its ability to spin. As a result, gas moves inward along shocks, making the center mass thicker and sometimes setting off rings or starbursts. The outer disk spreads and can make outer rings and faint extensions. It gets the bar's gift through spiral arms and resonances. All of this doesn't go against protection. The ledger is balanced, the halo gains from the bar's loss, the inner disk profits from mass coming in, and the outer parts save up for more spin. How strong is the effect? It hinges on three things: how massive and responsive the halo is in the region the pattern probes, how long the pattern holds a steady beat, and how much mass the disk or bar carries. A denser, more live halo absorbs more angular momentum because more orbits can resonate with the pattern and linger in the wake. A long-lived, steady bar can transact more because it keeps ringing the same halo orbits. A heavier bar has more to give in the first place. This is why simulations with fully responsive halos show bars slowing measurably, while models with rigid halos, where no wake can form, keep bars artificially fast. The exchange runs both ways. Fresh gas accreting with high specific angular momentum can, through spiral waves, give some of that spin back to the inner disk and even to the bar, briefly spinning patterns up or shortening them. But on average, the tide flows outward. Inner non-circular structures pass angular momentum to the outer disk and halo. That trend helps explain two observations at once: why outer disks often look extended and low in surface brightness, and why many bars exhibit signatures of slowed pattern speeds and grown lengths. You can see friction's fingerprints in stellar halos. The long, faint streams arcing around galaxies are not only debris from stripped satellites, they are also storage lockers for angular momentum. Their great distances and gentle orbital speeds tell you that much of the original orbital spin ended up parked far out. In the inner parts, where streams have phase mixed, the memory lives in hotter velocity distributions and thicker disks. Feedback moves angular momentum. Stars do more than shine, they also push. Gas gets energy and speed when big stars explode as supernovae, when groups send out winds, or when a black hole in the middle lights up as an active core. That stirring does more than just control how stars form. Angular momentum is also changed, which changes where gas can circle and how disks grow or shrink. You can think of feedback as a big hand on the galaxy's mixing spoon. It pushes low-spin gas out, puffs up, and swells the disk, and helps high-spin material take over the edges. Start with a gas-rich disk, forming stars quickly. Supernovae go off like space depth charges, each carving a hot bubble that expands and then bursts into the surrounding medium. The expansion accelerates gas and adds random motion, which raises the disk's effective pressure support. In angular momentum terms, that extra stirring can keep gas aloft at larger radii than it could reach with rotation alone. Bubbles that vent out of the plane become chimneys that carry low-spin material away from the midplane. When that gas cools and rains back down at larger radii, it returns with more angular momentum per unit mass, helping the outer disk grow. This fountain cycle moves spin outward without a clean conveyor belt. It is a messy but effective migration. Feedback also edits who gets to stay near the center. The gas that sinks deepest tends to be the lowest angular momentum fraction. Starbursts and nuclear activity attack that inner reservoir first, heating or ejecting it. Removing central low-spin gas raises the average specific angular momentum of what remains. Over many cycles, a galaxy can look as if it spun up, even though the total angular momentum in all phases, including the wind, is conserved. The key is selection. Keep the high-spin gas, lose the low-spin gas, and the surviving disk gets broader. On larger scales, active nuclei do similar work with a bigger hammer. A black hole that gulps gas can unleash radiation, winds, and jets. These outputs couple to the halo and the disk, driving outflows that escape or at least stall infall. If the outflow vents along the minor axis, it avoids stripping the outer high-spin gas that supports the extended disk. Instead, it preferentially clears the central regions where low-spin gas had piled up. In some systems, radio jets inflate cavities in the hot halo, stirring it and preventing it from cooling smoothly. That keeps the inflow rate low, starving the center, while cold filaments at high angular momentum may still trickle in along protected lanes. Superbubbles and winds also seed torques. As a bubble expands in a rotating disk, it sweeps up gas and forms shells that do not share exactly the same angular momentum as the pre-existing gas at that radius. Where shells overlap, pressure gradients and shear drive flows that exchange angular momentum between neighboring annuli. Over time, that shuffling can smooth sharp features in the radial profile, spreading gas outward and changing where stars form next. The effect of feedback on rotational momentum can be seen statistically because it is messy. Simulations of galaxies with strong, bursty feedback tend to be more like the real thing. Disks are bigger at a fixed mass. Low-mass galaxies keep more specific rotational momentum, and the scatter in the spin mass plane matches measurements. Without input, systems with low mass cool down too much, pack too much low-spin gas into small areas, and become too close together and slow to spin compared to real dwarfs. When you give input, fountains and winds keep the angular momentum budget from falling inward and let thin disks form by letting enough settle. Flows that go out don't always come back. Some winds reach escape speed and carry angular momentum all the way to the halo or further. That doesn't break conservation, it just moves the spin around. The halo gets that rotational momentum, which can change the shape of later cooling flows when they arrive. When the hot medium is thick in group and cluster settings, outflows pick up more mass and often stop. This creates a moving pool that slowly moves back to the disk with more specific angular momentum than the gas that left. Bars and circles can also be affected by feedback. As gas is shaken along a bar, supernovae can push it up just as it tries to cross resonances. Adding pressure can slow down the flow of water, which can change where the inner bands form. If, on the other hand, feedback has reduced center densities, a bar may have a weaker frictional partner in the halo and slow down less, which changes how much rotational momentum it sends out. Because of these crosstalks, you can't just think of feedback as a story about how stars form. It's also a way to move angular momentum around. Accretion disks move angular momentum. Disks can only build up if something moves with rotary motion outward, letting gas inside fall in. If circles are left alone, nothing happens because each ring keeps its own spin. Stress is the key. Tiny pushes between bands that are next to each other that trade rotational momentum. This is done by viscosity, which is the internal friction that lets one layer slide on top of the next. Because cosmic disks are too dense for simple molecular viscosity to work, nature builds a bigger engine. Turbulence and magnetic fields that make a viscosity strong enough to change the shape of the flow. The classic language is simple. Picture the disk as many thin rings. A ring slightly farther out orbits more slowly. A ring slightly farther in orbits faster. If stresses connect them, the inner ring pulls backward on the outer ring, giving it angular momentum, and the outer ring pulls forward on the inner ring, taking angular momentum away. The outer ring drifts outward a little. The inner ring drifts inward a little. Repeat this exchange everywhere, and you have a steady conveyor. Angular momentum marches outward, mass drifts inward, and the disk accretes. How strong is that stress? Astronomers wrap the messy physics into a single, dimensionless knob called alpha. Narrated in words, the R-phi stress, the shear stress between adjacent rings, is taken to be alpha times the local pressure. If alpha is a small number, transport is slow. If alpha is a few tenths, transport is brisk. This alpha prescription does not care what makes the stress. It just measures its effect. In real disks, alpha comes from turbulence and magnetic tensions rather than simple friction. Magnetic fields unlock the main instability that keeps many disks alive. The magnetorotational instability, or MRI. Take a weak magnetic field connecting two fluid parcels on neighboring orbits, one slightly in, one slightly out. The inner parcel orbits faster, the outer slower. The field line between them acts like a spring. The inner parcel pulls ahead, the spring stretches, and tension drags it backward, robbing it of angular momentum so it sinks inward. The outer parcel lags, the spring pulls it forward, it gains angular momentum, and it moves outward. The small difference in orbital speed feeds the spring, which strengthens the difference further, a runaway that turns a quiet disk into magnetized turbulence. That turbulence produces both Reynolds stresses from fluid motions and Maxwell stresses from magnetic tensions, and together they realize the alpha stress the disk needs. The disk turns into a controlled machine as soon as the MRI wakes up. It gets a little bigger because of turbulent dissipation heating it up. Radiation cooling lets it lose that heat so turbulence can keep working without making the flow too hot. The width and temperature distribution of the disk are set by the balance. MRI works well in places where ionization is high, like near hot stars or in bright active galactic cores. MRI can be turned off in places where ionization is weak, like cool areas in protoplanetary disks. This makes dead zones with low alpha. Angular momentum can still be moved by vertical shear, baroclinic vortices, zombie vortices, and magnetic winds, though they do so more slowly most of the time. Disks also launch outflows that help. Magnetic fields anchored in the rotating disk can fling gas along inclined field lines, a magnetocentrifugal wind. In plain terms, field lines act like rigid wires. Gas slides along them and, beyond a launch point, feels a lever arm that extracts angular momentum. The wind carries that angular momentum away, allowing the footpoint gas to move inward even if turbulence is weak. In young stellar systems, such winds and related jets are not decoration. They are angular momentum exhaust, letting the inner disk feed the star. Around black holes, winds and jets can tap both the disk's rotation and the hole's spin, exporting enormous angular momentum and energy. Close to the center, the rules change by boundary conditions. Around a star, the disk meets a stellar magnetosphere. Stresses there can pile up gas, trigger bursts, or channel flow into funnel streams. Around a black hole, there is an innermost stable circular orbit. Inside it, matter plunges. The disk's stresses do most of their work outside that radius, loading the plunging flow with the right energy and residual angular momentum. Radiation from the inner annuli then tells you how fast the conveyor is running. Brighter means more gravitational energy turned into heat as stresses do their job. There are different kinds of accretion disks, but the transfer story is always the same. The same alpha-style stress causes outburst cycles in cataclysmic variables and X-ray binaries. When the disk gets hotter and more ionized, MRI moves better, accretion rises, and the system gets brighter. When it cools, transport slows down and the disk fills back up. In busy galactic nuclei, broad spectral energy distributions and reverberation maps show that big radii feed steadily while stress-heavy core zones heat up. Measured rates of accretion onto young stars, gaps and rings in millimeter pictures, and wind tests all work together to put limits on alpha and the role of magnetic winds at different radii. Magnetic braking and protostellar outflows. It's hard for a thick core that's about to become a star because it has a lot more rotational momentum than a single star can hold without spinning apart. When things fall apart, something has to let most of that spin escape. Nature's answer is to change gravity's straight fall into an agreement based on magnets. In a collapsing gas, threads of magnetic field connect it to its larger surroundings. These threads act like torque lines, pushing angular momentum outward and sending some gas into fast collimated streams that remove angular momentum. A molecular cloud core starts to spin a little. It spins faster as it gets smaller, like how a dancer's arms turn faster when they are tucked in. The heart is not alone, though. It is held together by magnetic fields that come from the parent cloud. As the gas tries to spin, these fields connect the faster-moving material inside to the slower-moving material on the outside. The twist is being fought by tension along the field lines, like a spring trying to unwind. The resistance pulls on the inner gas, taking away its rotational motion and putting it farther away. Magnetic stopping is the name for this process. It does not stop collapse. Instead, it keeps spinning from happening, which lets collapse happen. The efficiency of braking depends on how well gas and field stay locked together. In cold, dense cores, the coupling is imperfect, especially where ions are scarce. Three non-ideal effects, ambipolar diffusion, the Hall effect, and ohmic dissipation, let neutral gas slip past field lines to varying degrees. Narrated, they change how strongly the magnetic spring grips the flow. If coupling is too strong and geometry too simple, braking can be so effective that it robs the inner regions of nearly all angular momentum, suppressing the formation of a sizable disk. If coupling is weaker or field lines bend and twist in more realistic three-dimensional ways, braking moderates, and a disk a few tens to hundreds of astronomical units across can form. In practice, turbulence, misalignment between the core's rotation axis and the field, and the infall of material with changing orientation all conspire to keep enough spin for a disk while still removing the bulk. Outflows and jets are the second relief valve. As a tiny disk takes shape around the forming protostar, magnetic fields anchored in the spinning disk can fling gas outward along inclined field lines. Think of a bead sliding along a rigid wire that is being spun. Beyond a certain point, centrifugal force wins and the bead is launched. In magnetocentrical terms, the field provides a lever arm. Gas leaving the inner disk carries away the angular momentum that would otherwise keep the remaining gas from spiraling inward. Close to the star, a second, tighter jet may tap the stellar magnetosphere itself. Both components act as angular momentum exhaust, and both show up early in life as narrow, high-speed flows that punch holes through the shrouding cloud. magnetic braking writes its signature on scales you can see. Disks around the youngest protostars are often small compared with those around older pre-main sequence stars, consistent with strong early braking that weakens as the envelope thins and non-ideal effects grow. Polarization maps of dust emission trace the curved magnetic fields threading envelopes and disks, showing hourglass shapes and twisted geometries that fit the torque story. Molecules tracing rotation reveal that outer envelopes turn slowly while inner disks turn faster, exactly what you expect when spin is being siphoned outward. The Hall effect adds a subtle twist. It can either help or hinder disk formation depending on whether the magnetic field points with or against the rotation axis. In simple terms, the handedness of the coupling matters. If aligned one way, the Hall term supports the buildup of a larger disk. If the other way, it enhances braking and keeps the disk smaller. This sensitivity may explain why otherwise similar cores give birth to a range of disk sizes early on. The spin problem still exists on the surface of a star after it has formed. Young stars form from an inner disk that is magnetic and often ends near a few stellar radii. You can use field lines to link the star to the inner disk and create a torque that moves the rotational motion back and forth. At times, this disk locking slows the star's spinning, even though accretion is still happening. At other times, the star can speed up if the link gets weak. At the same time, the star sends out its own magnetic wind, which takes away the angular momentum. This starts the long-term spin down that will last for billions of years.